Welcome everyone to today's colloquium and the second colloquium in our hybrid mode. So welcome everyone online too. We are going to start our colloquium, and it's an absolute pleasure to invite Professor Abhishek Dhar for the colloquium today. And it's particularly a great pleasure for me to introduce him. He's a colleague and sort of a go-to person for me for various issues about physics and other things. So Abhishek, of course, is one of the leading physicists in the area of non-equilibrium statmech and particularly out of equilibrium systems. And he has done extensive work in various issues regarding transport, particularly heat transport in low-dimensional systems, and various other things that you would talk about today in an aptly titled talk, Connections between microscopics and macroscopic laws, which is his area of specialty. So Abhishek did his PhD in TIFR and completed his PhD in 1998. And after that, he was a postdoc in IIC, RRI, and University of California at Santa Cruz. And after that, he was at RRI as a faculty. And then he joined ICTS, where he's now a colleague. And so Abhishek's work has been widely recognized, and he's a recipient of the ICTP Prize in 2008, the Shanti Swarup Bhatnagar Award in 2009, and he's a fellow of Indian Academy of Sciences, the National Science Academy, and the Indian National Science Academy. He would be talking about his work today. So before I hand this over to Abhishek, those online, please mute yourselves and please unmute yourself if you have a question during the talk, and ask a question. And at the end of the talk, we of course would have a question session. For those who are attending in person, please use the microphones that are there in the auditorium, because otherwise the online people cannot hear you. Okay, so with that, let me hand over to Abhishek for his talk.
Okay, people can hear me? Okay, so thanks, Shubhra, for the kind introduction, and thanks to you and Vishal for asking me to give the colloquium. So it's always nice nowadays to to be able to talk in a lecture room. Okay, so what I'll talk about is connections between microscopic and macroscopic laws, and there are two parts of the talk which I'll describe. Okay, so this is the plan of my talk. First, I'll just broadly say what exactly I mean by this. And then there are two parts, like I said, and the first part is something I've been interested in for a long time, trying to understand Fourier's law of heat conduction, which is a macroscopic law, and how do you understand it from my microscopic point of view. And then the part two is something I've been interested in more recently. It's called the blast problem, and it's basically trying to test this Navier Stokes Fourier equations, again, macroscopic laws in a particular setup. Okay, so please ask if you have any questions at any point, please stop and ask. Okay, so this is the microscopic point of view. If you take a box filled with water, and if you look closely, what you will see is that you have water molecules inside, and let's say if you're in a box of size something, you have n molecules, which are moving according to Newton's equations, right? If you're using classical description. So this system is completely described by Newton's equations of motion, mass into acceleration equal to force on each particle. And an alternative way of writing these equations is this Hamiltonian form, which is, so basically this system is described by a Hamiltonian, which has a kinetic energy and a potential energy. And then we can write these equations, the second order equations, as a set of first order equations. Okay, so this, I mean, if you know the initial conditions, initial positions and momentum of all the particles, then you know exactly how it evolves. And in some sense, we know exactly how the system is, everything about the system. But of course, this is not what we typically observe. I mean, what we observe typically is like if you take a gas, what you can actually measure is like you can put a thermometer and measure its temperature, or you can put a barometer and measure the pressure. And you can weigh it and find its density. And so this is the macroscopic description, right? In terms of variables like pressure, temperature, and density. And then we know that there are in systems in equilibrium, there are this equilibrium laws of, like, for example, thermodynamics, the first and second law of thermodynamics. And then there are interesting equilibrium macroscopic properties, like there's an equation of state which tells us that these three quantities are actually connected in a non-trivial way. And then there are other interesting things that you can measure in a system, like its specific heat and how compressible it is and so on. Okay, so these are like equilibrium, what you would think of as equilibrium properties of a system in terms of observables, which are macroscopic variables. Okay, so now there is a nice theory of equilibrium statistical physics, which tells us how these two descriptions are connected. And this is the theory that was built up by Boltzmann and Gibbs. And basically it tells us that if you, like, for example, look at the gas in this room, then you need a few variables to describe it. For example, its total number of particles, the total volume in this room, and the total energy of all the particles, and the total momentum. Okay, and these are like the conserved quantities in this of the microscopic dynamics. And these are all the variables that are sort of relevant. And then what Boltzmann and Gibbs tell us that is that so you have the microscopic dynamics is in a 6n dimensional phase space, and on this it moves on a constant energy surface because that's a conserved quantity. And supposing you compute the volume in this phase space between E to E plus delta E of the phase space volume in this of this energy shell, and I call that omega. So it depends on the energy, the volume, and the number of particles. And momentum in equilibrium is not relevant because I can always work in a frame where the center of mass is at rest. So once I compute this and then I define this entropy function, then in this function actually contains all information about equilibrium properties of a system. Okay, so I can find the equation of state, specific heat, compressibility, and everything. So it's quite amazing that we can have such a description, but this is what these people worked out. Okay, so this is equilibrium physics, but now let's look at things, macroscopic laws, which are sort of, which describe non-equilibrium phenomena. Okay, so these are like things which you already know are transport phenomena. So this is like if you put some ink and then it spreads, that there's some diffusion law. Then there's, if you have a fluid where different parts are moving with different velocities, then there's some shear force, and you can ask how does the shearing force depend on the shearing rate, and that is given by this Newton's law of viscosity. There's Ohm law of electrical conduction and Fourier's law of heat conduction. So this kind of laws describe the response of a system to sort of perturbations, like you put a temperature gradient and see how much current, and the system is going out of equilibrium, right? So, so these are non-equilibrium phenomena, and there are various macroscopic laws which try to describe these phenomena. And then there is a these are related descriptions. There is a hydrodynamic description, and for a simple fluid, so this I'll describe in more detail. You basically write down equations for this, what I call the conserved variables, which now you say are slowly varying in space and time. Okay, and there's a phenomenological way of saying how these fields evolve, and these are the Euler equations, Navier Stokes equation, and these equations, Navier Stokes Fourier equations, which I'll describe more in more details later. But these are like the macroscopic laws which describe non-equilibrium phenomena. Okay. So in this case, I mean, trying to understand this, you can't just directly use the Boltzmann-Gibbs formalism, which is adapted to equilibrium properties. And and then we don't have some such nice way to see the connection between the macroscopic laws and the microscopic laws. Okay, so this is what we want to discuss in this colloquium. Okay, so I'll start with part one, where I'll talk about Fourier's law and like how do you establish it from microscopics, and then we'll talk about the other second part. Okay, so Fourier's law, what is Fourier's law? If you take, like, this is an experiment which many of you would have done in the undergrad. You take a like a bar of metal and you put one end at steam and one end in ice. And then if you put a thermometer anywhere, you find that there's a temperature profile in the system. Obviously there's some heat current going through the system, right? So there's a temperature gradient and there's a heat current flux. And what Fourier's law says is that the current is proportional to the gradient of temperature, which seems like an obvious relation. If there's no gradient, there's no current. So it's the least, sort of the simplest thing you can write. And this proportionality constant is called the thermal conductivity of the material. Okay. So yeah, so this is Fourier's law, and this kappa, the thermal conductivity, is supposed to be it's a transport coefficient, which is supposed to be a property of the material. Okay, so it's an intrinsic property of the material, and if you use this and the energy conservation equation, so this epsilon is less than the local energy density in some in a region, then the rate at which this changes depends on the specific heat times the rate of change of the temperature. And then if you combine this with this, you basically get that the temperature field satisfies the diffusion equation. Okay, so Fourier's law basically implies diffusion of heat. Okay. Okay, so this is just some note on Fourier's. So this law was written, I think, around 1810 by Joseph Fourier. And he was, of course, quite an amazing person. I mean, he was one of the first person who started using partial differential equations to formulate physical problems. He invented Fourier transforms, of course, and we all hear now about the greenhouse effect. So this is something he first, in fact, thought about. And there's a very nice review article in Nature describing some of his work. So one of the first interesting applications of Fourier's law was actually trying to estimate the age of the Earth. So, this was done by Kelvin in 1862. So basically, that time, because all the geologists, biologists, they had various theories of how old the Earth was. It's a natural question, right? So, Fourier, this Kelvin thought of this simple model. So let's imagine that Earth started as a, sort of a hot uniform ball at 3000 Kelvin. Okay, so that's what we expect to be the initial condition when it was formed, and then it has been cooling, right? So how does so what is the cooling process? So you can imagine that outside is like at zero temperature. So basically, heat is flowing radially outwards, and so then how fast it cools obviously depends on the thermal conductivity, right? So if you just assume Fourier's the Fourier heat diffuses according to Fourier's law, and then use some known facts about the present situation of the. So this is the starting point, and let's say at present the Earth looks like this. It's sort of hot, cold, and there's some gradient in temperature. Okay. And it's known that if you go down into the Earth, the temperature increases by about 20 degrees Celsius per kilometer. So using this simple information about the present and what you expect of the past, and using Fourier's law, you can estimate the age of the Earth. Okay, so Kelvin did this, and he actually got this number. 200 million years. Okay, so this was quite. At that time, it was very. Remarkable idea that it can be 200 million years and people, of course, thought like maybe it's 6,000 years old, or and some people like geologists and all thought it should be much, much older. Okay, so this was quite an important idea at that time. Okay, so this was a historical note. So let's go back to the this main question. I mean, so this is a Fourier's law is a macroscopic phenomenological law. Can we derive this law from Newton's equations? Okay, so that's the basic question. So in 2000, there was and there's a article by these people, Bonetto, Debele, and Lebowitz, asking. The paper was titled "Fourier's Law: A Challenge for Theories," and this question was posed that I mean, can one find a simple model where you can prove this law? I mean, starting from complete scratch. Okay. And actually, the paper authors of this paper offered a bottle of very good wine to anyone who solves this problem. I mean, so far, no one has got this. Okay, so so now let's see what the simplest idea that one has of heat conduction is, of course, a picture in terms of kinetic theory. So if you think of a solid, let's say, so solid has like ions fixed at let's say lattice positions, and then you have electrons moving around. And let's say it's insulating, so the electrons don't carry heat. I mean, basically the vibrations of the lattice carry heat from this hot end to the cold end. And so heat is carried by phonons, okay? So now, why do we expect diffusion? So what one can imagine is that like if the phonons here get excited, then what they might do is that there's a lot of maybe disorder or there are interactions between the phonons, so they kind of do a random walk. Okay, so the phonons that you excite here kind of do a random walk, which means diffusion, and that's why that might be the underlying reason why you get diffusion. Okay, so you can do a simple calculation, like if you imagine that the heat carriers are doing a random walk, and then you can ask, like, what is the net flux of energy across across a slab like this? Then because there's more energy density out here than here, so you just multiply by the flux from this side and subtract the flux from the other side. And then you just assume that this energy density kind of changes slowly. So you do some Taylor expansion and so on. That immediately tells us that the current is proportional to the temperature gradient. And the proportionality constant depends on the velocity, the mean free path of these heat carriers, and their specific heat. Okay. So this is the simplest kinetic theory expectation, that the heat flux should be proportional to temperature gradient, and you get the thermal conductivity in terms of some microscopic properties. The mean free path, the specific heat of the particles, and their velocity. Okay, so it looks like you can actually derive Fourier's law, but this is not really a proof because you're assuming diffusive motion for the phonons, right? Okay, so now I should say that there are other more sort of formal approaches of trying to understand thermal conductivity and trying to compute this unknown quantity in terms of microscopics. So the main unknown quantity is the thermal conductivity, and this is something we would like to compute given a Hamiltonian, right? So so there's this theory called Piles-Boltzmann theory of phonon heat conduction, and which tells us that it's a sort of it's just some improvement of the kinetic theory, where you sum over all possible frequencies allowed in the solid, and the basic quantities are some mean free path and a velocity and specific heat and so on, and density of states. Okay, so so then where does the connection to the microscopics is that the mean free path has to be computed from some perturbation theory. Okay, given a specified Hamiltonian. Then there's something called linear response theory, which is again a perturbation theory of, like, you take a equilibrium system and perturb it, put a electric field, small electric field or a small gradient in temperature, and ask how the system responds. And what this theory tells you is that the conductivity is given, can be expressed in terms of some equilibrium correlation functions. Okay. Okay, so these are perturbative theories, and so one would still like a more rigorous derivation than this. Okay, so this is the basic question. So let's ask, what is the most direct way that you can try to verify Fourier's law? Yeah.
So we have gone through different approaches.
Yeah.
What is wrong with those approaches, and we are going to something else?
So I said it's a perturbative approach, right? So you don't know whether you're getting the right answer or not. Like that's the problem, of course, with any perturbation theory. The other approach was, like I said, you assume diffusion, so obviously you'll get diffusion. So it's not a derivation. So we want to do something more basic. Okay, so let's ask what is the most direct way one can imagine, right? So if we think, okay, so let's take the simplest system. Let's take a one-dimensional chain of particles like this, which are evolving through Newtonian dynamics. And we want to connect them to heat baths at 2 different temperatures, right? So this is a system described by them. Now I'm looking at one-dimensional systems. So there's a kinetic energy. This is interaction between nearest neighbors. And I can also put some external potential if I want. Okay, so this is the basic Hamiltonian that I'll be talking about most of the time. It's a one-dimensional system. And the dynamics is, if you look at the bulk particles, so there are n particles from 2 to n-1 just satisfy Newton's equations. So mass into acceleration is equal to force. For the boundary particles, particle 1 and particle n, they have a slightly different dynamics because they're attached to heat baths, right? Because they're interacting with some cold or hot. And the way to model this is by writing this sort of Langevin equations for the first particle. So this is a standard way of modeling a heat reservoir. There's a dissipation and there's a noise term, and they are related by something called fluctuation dissipation relation, in such a way that this bath, what we'll try to do is try to equilibrate the system at temperature T left, while on the right, this dynamics is trying to equilibrate the system at temperature TR. Okay, so this is where I put the temperatures at the 2 ends. Okay, so now this is the dynamics of a system connected to heat baths, and I just want to understand the from this what does it predict? Okay, so now I have to ask, like, what do I mean by temperature? What do I mean by heat current? Right, those are the first things that one has asked. So if I ask temperature, then I know that temperature is basically is related to the mean kinetic energy of particles. So I mean, this is something that I can directly measure, and that I can use to define the temperature at a local point. Right, so just the mean kinetic energy of particles at every point. So that gives me the temperature profile that I'm looking for. And then I want the current. And so how do I find the heat current that is going across the chain? So like usually what you do to find a current is like you define an energy density and try to write a continuity equation, right? You take the energy density, do del A, del epsilon, del T, and you find that it can be written as divergence of some current. Okay, so that defines the current operator. And in this case, the current is just given by velocity of a particle times the force that this particle exerts on this. Okay, so that's actually the microscopic current. Okay, and I just take average of that quantity, and that will give me the average current going through the sample. Okay, so starting with this completely microscopic dynamics, I can calculate these quantities, and then I can basically ask, is this law valid or not? Okay. So, so the idea is that I measure the heat current. So I take a system with n particles of, and then let's say this length L, and I measure the heat current. And what Fourier's law implies is that the current should scale with difference in temperature, and it should scale as 1 over the system size, right? So this is what we want to show. Is this true or not? And this will also tell me what is the thermal conductivity. So once I verify that this is true, that the current scales as 1 over L, then the thermal conductivity is just J times L divided by delta T. Okay. Now this delta T is something, if the temperature difference is small, this is easy to prove that this has to be true. But what is difficult to prove is that this 1 over L size dependence. Okay, so this is, I mean, kind of intuitively it seems obvious that, okay, if I increase double the system, the current should go down half. But it's not something that's easy to prove, and in fact we'll see it's not always true. Okay, so now what we'll see is that most often what we have to do to the simplest thing we can do is to start with is just to do a simulation and see if is this true or not. Okay, so we want to take a system of size L and measure the current, then increase the system size, measure the current, and see how it scales with system size. and if this is true, and then find the conductivity, okay, and see if this is independent of system size. Any questions? Okay. Okay, so now I'll just tell you what the results so far are. In fact, so direct studies and simulations and some exact results in 1 and 2 dimensional systems find that Fourier's law is in fact not valid. And surprisingly, the thermal conductivity is not an intrinsic material property. Okay, so it depends on how large a system you take. So the thermal conductivity in 1D systems diverges in some way as a power law. In 2 dimensions, it's probably a logarithmic divergence, while in 3-dimensional systems, you find it's finite. Okay, so this is typically for anharmonic systems without disorder and with momentum conservation. Yeah,
Abhishek, in the previous slide, like this J in the Fourier's law, is it measured at some X or?
it is measured. So if you are in a steady state, of course, it should be independent of X, right? The same, because of conservation, the same current should go at any X. I think it's on.
Okay. So when do we get log L divergence?
Into 2 dimensions.
Okay. I mean, what kind of system?
I mean, it's supposed to be universal, right? Yeah. I think there's also... Okay, yeah. So the question is, I mean, when I say anharmonic systems, does it have to be integrable? Is there a difference between integrable and non-integrable systems? So yes, the answer is that these are for non-integrable systems. So these are, I mean, yeah. So this I'll of course explain later. But these are for generic systems which we expect to be non-integrable.
And this result is true regardless of whether you consider long-range interaction or short-range?
No, this is short-range systems, right? Yeah, in systems with short-range interactions. Okay. Okay. So I think probably I will only finish part 1 of my talk, but that's okay. Okay. So I just want to say that I mean, of course, people might be worried about is this true in real systems, and yeah. I think it's working.
Yeah, it is now okay. Just go to the previous slide. In for the 2D, what that we write that L power alpha prime, because if it is already log L.
Because there is some controversy about whether it's a very weak power law, it's a logarithmic divergence. So I just wrote that.
The mechanism behind thermal conductivity is something related to, you said something related to the collisions and relaxation time of phonon, something like that.
Yeah.
But how it different from dimensions to dimensions? If you are going to higher dimensions or lower dimensions, what happened to this mechanism? That's why this change must have been occurring, right?
Right. Yeah. So all this I'll explain hopefully during during the talk. So this I just sort of give a summary of main results, but I'll try to explain some of the aspects at what we understand kind of why this happens and so on. Okay, so I just want to point that I mean you can there are very few experiments which have tried to see this kind of divergences in systems like nanotubes and nanowires, which are the natural candidates for like 1-dimensional or 2-dimensional. So this was one of the first experiments, and there's a more recent experiment in I think 2017, again on nanotubes, which saw this kind of divergence in thermal conductivity. Okay, so this you see a thing which is suspended. I mean, you put heaters here and some cold bath here, and then just find the current. Okay, so and then there are some reports that graphene, which is known to have extremely large thermal conductivity, might have a size dependence conductivity like this. Okay. So here I should say that, I mean, for example, there's something called Marmin-Wagner theorem, which tells you can't get a crystal in 2D. But of course, you can see graphene is a nice crystal, right? So, I mean, there's questions of scales and all where you expect to see these divergences and so on. So it might be, some of these things might be difficult to see in experiments. But in principle, it's something that just follows. Okay, so let's start now by explaining like what are the models for which things have been how we arrive at these conclusions that I just mentioned. So first, let's start with the simplest system that you can think of, a harmonic chain connected to baths. So this is the Hamiltonian, right? Just a quadratic, purely quadratic interactions. Okay, so this model was first studied. I mean, this was one of the first models ever studied by these people, Ryder, Lebowitz, and Lieb. And so given this Langevin baths at the ends and this Hamiltonian, you can actually solve exactly the steady state of the system. It's a highly non-trivial result. But once you find this non-equilibrium steady state, from that, what you can extract is the temperature profile and the heat current. Okay, and what they found is that the current does not depend on system size. So there's no 1/n scaling. And the temperature profile is completely flat inside. Okay, so no temperature gradient. Okay, so this is of course surprising. Fourier's law for the ordered harmonic chain, or in this is true obviously in any dimensions. Actually, there's Fourier's law is not valid for a harmonic crystal, and this is also the case for other integrable models like ideal gas, Toda chain, and Tong's gas. And this can be understood as basically like when you send heat, means it's phonons going through, and there should be some scattering mechanism, right? So this is what the picture I described you right at the beginning. So there should be something to scatter the phonons. So you can think of two mechanisms. Maybe disorder can scatter phonons, or you can have phonon-phonon interactions. Okay, so now we'll try to see what the effect of these two things are on heat conduction. Okay, so so let's put a disorder. So this is the heat conduction disordered harmonic chain. And the easiest way to put disorder is like you can make the springs random, or you can make the masses random. Okay, so this is then the Hamiltonian. It's still a quadratic Hamiltonian, but this masses could be random, or the spring constants could be random. Okay, and then you can so you should just note that this term, which represents an external potential, I'll call that the pinning sort of a pinned system. Okay, so it's like if it's sitting on a substrate or something. Okay, so there's a distinction between pinned and unpinned systems. So just keep note of this nomenclature. Whenever I have such a term, it's called a pinned system. Okay, so now we ask what happens in heat conduction. There's some way thing to scatter the phonons. Does it give Fourier's law? Okay, so in this case, it turns out that again, there's a very nice formalism that to compute, to understand the system, you can write an exact formula for the heat current, which is called a Landauer formula in terms of phonon transmission. Okay, so this is still a non-interacting system. So you can just think of you are sending phonons and they get transmitted with some transmission coefficient. So it's just sending like a plane wave and asking how much of it gets transmitted. Okay, and then you just integrate over all frequencies that are allowed. Okay, so you have this simple formula, and in fact you can write this formula in the quantum case also. And so we just need to analyze this formula for a particular, let's say, disorder, kind of disorder. Like given this purely harmonic system, how do phonons transmit across this system? Okay, so so we have to understand in particular how this depends on, how does transmission depend on the length of the chain. And in this case, we have to understand what is the character of the normal modes in the system. Okay, so for a harmonic system, you can always go to some normal mode description where you think of isolated oscillators, right? And so we can ask what is the character of the normal modes in this kind of a disordered system. And that will actually determine what is the transmission at different frequencies. Okay, so given a chain of size n, there are n normal modes at n frequencies, and we can ask what is the property of these modes. Okay. So in this kind of system, something called Anderson localization occurs, which actually determines the properties of the modes. And what you find is, let's say I've drawn this picture in 2 dimensions. But basically, if you look at if you take, let's say the masses are random and you just look at the normal modes, you find that they can be of 3 kinds. Something called ballistic modes, which look like plane waves, which extend across the system. Then there are modes which are like diffusive modes, which are extended but sort of random. And then there are modes which are look like this, which are completely localized. Okay. So in one dimension, it turns out that almost all modes are like this. And then there are some modes which look like this. Okay. So there are, at the very low frequency, there are some modes which can carry energy, right? You can imagine if there is a mode like that, if you excite it at this end, it can carry energy, but this guy cannot transmit energy. Okay, so from this picture, what one finds is that using basically this idea, and then one can compute what is this transmission, how does it depend on omega. And basically, one finds that it decays exponentially with the size of the system, except at very low frequencies where it can transmit. And then you have to basically integrate over those low frequency modes. And from this, you can pull out the system size dependence of the heat current. Okay. And you find strange things. You find that actually it depends on what you do exactly at the boundaries. Like there's something called fixed boundaries and open boundaries, and you get different system size dependence for the heat current. And if you have a pinned system where you don't have any low frequency sound modes, then you find that the current decays exponentially with system size. Okay, so that's a heat insulator. Okay, so so this is what you find. I mean, so recently with Junaid and some others, we have done some interesting work on this system in magnetic fields, where again this kind of same physics can be seen. Okay, so this is the summary of with disorder. The main idea is that I mean almost all normal modes are localized and they don't carry heat. And the basic idea is that you don't get Fourier's law again, and you have strong boundary condition dependence. So in fact, you can also study the same problem in 2 and 3 dimensions, and you find that Fourier's law is still not valid in the unpinned system. If you have pinning, then you find it's actually, it's one of the systems where you can verify Fourier's law. Okay, so now we have looked at effect of disorder, and we see that we still don't get Fourier's law. So now let's try to put in phonon-phonon interactions, which you can do by putting anharmonic terms in the Hamiltonian. Okay, so this is what are harmonic terms, and anharmonic terms you can put in various ways. So you can put, for example, a quartic potential at each site. Okay, so this is a system which will because this is an external potential. So it's a pinned system, and it doesn't, total momentum is not conserved. Okay, so you should remember this important distinction between momentum non-conserving systems and momentum conserving systems. So pinned systems don't conserve momentum. And so this is the nonlinearity here. And in this case, you find, again, just from simulations, that Fourier's law is valid. Okay. Now let's look at this other famous model called Fermi-Pasta-Ulam-Singao model. Where the nonlinearity is of this form, cubic and a quartic nonlinearity. So by the way, this model is usually called FPU model. This person, Singhao, I mean, she did all the simulations, okay. And then and at that time, people thought, okay, simulations, I mean, it's not so important. I mean, so she never got credit for a long time. But now it's this model is usually referred by the full year. Okay, so in this model, again, it was studied first to understand thermalization, why thermalization works, why statmic works, and so on. But one can also just study heat conduction in this model. I mean, it's one of the simplest toy models you can think of. And here you find that Fourier's law is again not valid. So in spite of putting interactions between the phonon scattering and so on, you find that the thermal conductivity actually diverges with system size as L to the power 1/3. Okay, and this is actually this power 1/3 is kind of universal. You can change the interactions here. There are different models you can study, but you always get this power 1/3. And so this is what I'll call anomalous heat transport. Okay, so this is what is seen in momentum conserving systems without disorder, with just interactions, and the interactions are typically non-integrable. And you get this universal behavior, which violates Fourier's law. Okay, so I mean, so I'll just talk about some other signatures of anomalous transport. So I mean, so this is the setup. You just measure the current, and you find the divergent thermal conductivity. And so this is like what you do in a simulation. You measure this kappa for different system size, and you find this kind of a divergence. The other thing you can ask is, what does the temperature profile look like? And typically in such in systems like this, you find that the temperature profile always has this sort of singular structure. Okay, so there's particularly at the boundaries, you find some singular structure with the divergence in the derivative.
Abhishek?
Yeah.
Yeah. The upshot from this, the previous discussion is that if you have low energy density of state,
Yeah,
then Fourier law is violated.
Right. Yeah. Even so, if you for the unpinned system, you always have low energy density.
Yes.
Yeah. So, but it's still so this. I mean, this statement is of course for even systems which have a low energy density of state. So, in fact, the divergence comes basically from the low energy modes.
So the I mean, basically the upshot is that all the systems that violates Fourier's law have low energy density of state as long as you pin the system. Fourier's law.
Right. Yeah.
But
right. Yeah.
But I mean, this is irrespective of how small the density of state is.
So I mean, this would be like the density of states. Of course, you are talking of the harmonic system, and there it will be. Yeah, I think. I mean, if you could kill the low frequency mode somehow, okay. Now you're asking how much you have to kill them.
So suppose I think about the low energy density of state to go as omega to the power alpha, and so for arbitrary.
Right. Yeah, I would imagine that. Yeah, if you have some really strong power, like high power, it should probably work. I mean, right. Yeah. I think so. Yeah. But I don't know of an example where how to cook up such an example. Maybe it might be possible with some interactions. Okay. Okay. So yeah. So this sort
Abhishek, I had a question. Now, can you hear?
Yeah.
Hello.
Yeah.
Yeah. So no, this definition of temperature you showed in very earlier for the just ordered harmonic chain. So that was just the average kinetic energy. So there was also, you assume some sort of a local equilibrium sort of thing, right?
Yeah.
So that definition is still valid for these FPU and other anharmonic chains?
So that's the definition. Of course, you have to use some definition in a non-equilibrium setup. Then you can ask, is local equilibrium valid or not? So typically in such systems, local equilibrium is, you can verify that it is satisfied.
Okay. Okay.
Okay. So you would like what it means is like, for example, you use the second moment of velocity to define the temperature. Now you can ask, you can compute, of course, the fourth moment. Is the same temperature from that definition? Do you get the same temperature, right? And you find that it does give you the same temperature. Or you could just plot the velocity distribution and ask, is it Maxwellian? It can't be exactly Maxwellian, but it will be very close to Maxwellian. Okay. So these are some. So the other signature of transport that you can try to look for is like, see this, when you talk of heat diffusion, what you typically expect is that you take a system in equilibrium. If you dump in some energy, it should spread like a Gaussian wave packet, right, diffusively. So now for this anomalous system, if you do the same experiment, if you take a system like this FPU chain, which is in thermal equilibrium, and put some excess energy and ask how it spreads, you find that it's kind of spreads super diffusively. So what this suggests is that this is actually, this system is, the heat carriers are not doing a random walk, but are actually doing a Levy walk. Okay. So, so this is some other thing that you can measure. So, and then you can measure, for a system in equilibrium, you can measure correlation functions of fluctuations. So let's say a system in equilibrium, there are constantly thermal fluctuations. So sometimes you find a lot of energy at some place. You can ask, how does that decay, right? So that decay, again, you'll find that it has an anomalous decay. It doesn't decay diffusively, but it decays like super diffusively. Okay, so this is another quantity that you can try to measure to understand anomalous behavior. And we'll see that I mean, if you put excess heat, what you'll find is that there's a central part which diffuses like slowly, but then there are some sound peaks which diffuse, which sort of move faster and carry a lot of energy. Okay, so yeah, so this is what I mean by this. I mean, so in a diffusive system, if you put a heat pulse, this is how it spreads. But in a FQ chain, if you put a heat pulse, you find that it has a peak, and then it has this. So these are the wave, the pulse at different times. Okay, so at early times it looks like this, then at later times it looks like this, and then even at later times. So you can see there's a sort of what I call a sound peak. So some of the energy just gets transmitted very fast, and some of the energy is kind of spreading slowly in the bulk. Okay, and this entire function actually fits to what is called Levy distribution. Okay, so this leads to basically the picture that one now has is that in these systems with anomalous heat transport, the heat is not diffusive transport, but it's actually a Levy walk. So, so what is a Levy walk? Levy walk is basically like a random walk is you take short steps at every time interval. For a Levy walk, you choose a time. So you can think, just imagine your phonons. They can go in the same direction for a long time without scattering. So there's like a long path, unscattered path, and then you again change randomly in some direction. Okay. So the distribution of steps sizes is kind of long ranged, and usually they are drawn from a distribution with a power law tail. Okay. So you have, so this defines a Levy walk. So there's some exponent beta here. And with this model, you can compute various things, like you can put Levy walkers at some with different densities in two reservoirs and ask what is the profile of density. And okay, so here I just show a random walk and a Levy walk. You can see that Levy walk moves much more than a random walk, and the distribution is basically this is a Levy distribution with a width which grows super diffusively. Okay, so this exponent beta tells us how the width grows. So this exponent beta was the exponent of the this hopping distribution. And that fixes like how this thing spreads, right? If you put a little bit heat, how fast it spreads. You can guess, right, which is Levy walk. I mean, the red is random walk. It spreads much slower. The Levy walk will do crazy things, and it spreads much faster. Maybe I should have a better picture. Yeah, this doesn't show. Yeah, okay. Yeah, so this is like the Levy walk sort of captures what we saw for the heat pulse. And you can do other things like you put reservoirs at different densities and put Levy walkers and ask what is the density profile. You find that the density profile looks almost like what you saw in the FQ chain. Okay, so again, you get the same kind of singularities at the boundaries and so on. It also gives you this exponent. So there's a lot of stuff you can extract from this simple phenomenological model of what's going on in this anomalous diffusion systems. Okay, so now it's always nice to, I mean, this, of course, this is a phenomenological picture, but it's always nice to cook up simple models which you can solve exactly. And in this case, the one such model is a stochastic model, okay, which was defined by these people. So the model is very simple. I mean, you take a harmonic chain and you have the Hamiltonian dynamics, which is of course trivial and doesn't do much, which we saw earlier. But now you put some stochastic rules, okay. So the stochastic rules is that you take nearest neighbors and exchange their momentum at some rate gamma. Okay, so now this model is interesting because it has the same conservation laws as your nonlinear models. It conserves momentum, it conserves energy, it conserves the number of particles. So it keeps the important conservation laws intact, but you can solve this model exactly. Okay, and in fact, this is a model where you can also derive the Euler equations, the hydrodynamic equations exactly. This was done by these people, and in this case, what you can show is that for this model, the temperature field, it actually satisfies this fractional diffusion equation, which corresponds to what you have for a Levy walk. Okay, so this can be proved exactly both on the infinite and the finite domain. And if you're wondering what this fractional derivative means in Fourier space, it's very simple. It just means that you take like k to the power 3/2 instead of k square. Okay, so so this is really nice because I mean you see something like from simulations, from phenomenology, and then you can prove this exactly in some simple model. Okay, so finally, let me just say that, okay, so we have some picture from simulations, some exact results from model. And the basic picture is that for systems, we have this anomalous transport, these systems with momentum conservation and some nonlinearity. Yeah. Not visualize, I mean, mathematically described, right? Yeah. I mean, that's no only way. I mean, of course, you have a discrete model I defined, right? Like random walk, you can define dynamics in terms of hopping rules, right? And then you can write a diffusion equation to also describe random walk. So it's similarly for the Levy walk, you can have a discrete like dynamics which tells you that it hops in such certain way. But then for the probability distribution, you can write a Fokker-Planck like diffusion equation, a fractional diffusion equation. So it's just two different descriptions. It's in the continuum limit, of course, right? Yeah. Okay, so now is there any other analytic understanding of this, what is going on in the system? And it turns out that is there like we just want to connect the Hamiltonian with what we are seeing in this heat transport experiments. And it turns out that our best current understanding is in fact based on, again, a coarse-grained theory called nonlinear fluctuating hydrodynamics. Okay, so so what is this theory? So this theory basically is you write equations for the three conserved fields. So in this equation system, one of the important points is that there are just three conserved quantities: the number of particles, or the density is the corresponding field, the momentum, and the energy. Right? These are the three conserved quantities. And the hydrodynamics idea is that you write equations for these conserved fields, and then you can write like you can make predictions for equilibrium correlation functions. Okay, so this was actually first this idea of using this hydrodynamics to understand anomalous heat transport was proposed by Anuttam Narayan and Sriram Ramaswamy in 2006. And some more details were given in this by this paper. And then a very complete theory was worked out by Herbert Spohn. Okay, so in a nutshell, this is the idea. You write these hydrodynamic equations for the three fields. So what I have here in black are called the Euler equations. Then the red terms are called Navier Stokes corrections, which is like viscosity and thermal conductivity. And then these are like noise terms, okay, which you want to which you have to add if you want to describe fluctuations in an equilibrium system. Now, starting from this, you can solve this equation somehow and compute correlation functions. Okay, and so I won't go into the details, but basically the prediction of the theory is that if you put a heat pulse, it has two peaks. It has a central peak which behaves like a Levy distribution, and then it has two traveling peaks on the side, which are given by something called KPZ scaling function. So this is quite a beautiful theory that emerges from this hydrodynamic theory, fluctuating hydrodynamic theory. And the nice thing is that it tells that the heat, whenever you put a heat pulse, there's this Levy, the central part which evolves like a Levy distribution, which means super diffusively, right? Okay, so so this is something we made a very detailed simulation, numerical simulation, to verify the detailed predictions of this theory. So if you do a simulation of the Fermi-Pasteur-Ulam chain, what you'll find is that So this is like what how a heat pulse spreads at different times. Okay, so at time 800, you find that there's a lot of energy here, and there's a lot of energy on two side peaks. And after some time, these side peaks are traveling at constant speed, while the central peak is spreading very slowly, right? Now you can ask, like, what you can do is you can try to put these three curves together. So you move them at the same origin, and then you do some scaling, which is given by the theory. Okay, so you try to check what the theory predicts, does it work? And you find that actually, so this is for the sound peaks. After you move them together, these three peaks, and then do some scaling in X and Y directions, you find that all the curves collapse into some nice curve. And this curve is given by some function called the KPZ scaling function. So this is quite amazing that it works so beautifully. And then the central peaks, if you again bring them to, if you do some scaling, they collapse to a Levy distribution. Okay, so now this hydrodynamic theory is quite amazing. It works for lots of other one-dimensional systems like rotors, nonlinear Schrodinger equation, Heisenberg spin chains, and so on. It tells us that you have anomalous transport in all these systems.
So that scaling behavior is true for all microscopic models.
Which this?
The KPZ and the...
Yeah. So I mean, for if you take a Heisenberg spin chain or a nonlinear Schrodinger equation, for all of them, you have the scaling functions are exactly the same. And even like the predictions are for even the scaling parameters, the theory tells you how to connect it from microscopics.
Because in the first part of your talk, the exponents were rather different for different models, right?
So no. So I said this 1/3 exponent was universal, right? 1/3, there was an exponent 1/3, which kappa goes as L to the power 1/3, right? That was, of course, I said it's universal. And similarly, many of these things are like completely universal.
But for different dimensions, like
dimensions, this is all one dimensions, momentum conserving systems. But you can change your microscopic Hamiltonian. It's universal in that sense. Of course, it changes with dimensions. So all I talk about is one-dimensional systems. I mean, 2 dimensions, of course, you have anomalous transport, that is, but the details of like scaling functions and what you expect is not known.
like given a dimension, the alpha, like how this J scales with L for different models are same.
Yeah, for a large class of models, right? Yeah, I mean, like if you take, I mean, if
without regards to integrability and all.
huh?
Without regards to integrable system or
not. No. So leave out integrable systems. I mean, so integrable systems are very special, right? Very special points. So you have to leave out integrable systems. So I'm talking only of non-integral Hamiltonians.
Question: in this fluctuating hydrodynamics, is it possible to have some colored noise instead of noise?
You can add, but then you can't do anything. You can always add. But first of all, yeah, I mean, when you like, you can try to derive it fluctuating hydrodynamics from completely scratch. Then what you get, in fact, is probably colored noise. But then you can't do anything, so you just make it white noise. And but then a lot of things still work, right? Yeah.
Yeah. How do you derive these lambda parameters from the theory?
So this the scale parameters. Right.
Does it depend on the coarse graining in some way?
No. So so this is quite amazing that this lambda S and lambda E. There's a formula, like if starting from your microscopic Hamiltonian, you can just determine them.
But is there any coarse graining dependence in this theory?
No. It doesn't depend on coarse graining, nothing. Yeah.
Is that specific to 1D or?
This is, of course, what I mean. I completely 1D. I don't know that. So this theory has not been developed at this level for in 2 dimensions, where also you expect anomalous transport. But there it has not been developed at this level of detail. So I don't know. I mean, what happens in 2D? Yeah. Right, yeah. So it's space-time noise, right? So it's there everywhere.
So does that mean the model is not
Yeah.
does that mean there should be everywhere or
No, oh, the noise means in the Hamiltonian dynamics is completely deterministic dynamics, right? There's no noise. But this noise is coming because of coarse graining, right? When you derive hydrodynamics, you have to coarse grain, right? So that's leading to like all this dissipation and noise. Okay, so I think I'm running out of time. So I'll just try to summarize. Shubhro, is that okay?
Yeah, maybe a couple of minutes.
Okay. So I'll only do part one. So unfortunately, because I was really, okay, yeah, part two is gone. So this, I don't even talk about part two. So let me just go to the summary. Okay, so yeah, so what I've tried to show is that deriving Fourier's law rigorously is a surprisingly hard problem. And it actually seems to be not valid in low dimensional systems. And this is what we called anomalous heat transport. The thermal conductivity kappa is not an intrinsic material property in these systems, at least. So it also we showed that therefore the diffusion equation is not valid in such systems, and alternative description is in terms of a fractional diffusion equation. And sort of microscopic derivation. So I'm not sure one should call it microscopic because we are using, in fact, hydrodynamics to derive it. But at least it gives some detailed understanding of correlation functions in this system is based on this nonlinear fluctuating hydrodynamics. Okay, and maybe I'll just tell you roughly what the idea of the other talk was that so in the other problem, what we study is if you take the gas in this room, you can have a Newtonian description. And let's say you look at an initial condition where you have a, let's say there's some bomb blast here, and you want to understand how it evolves, right? So of course you can solve Newton's equations for all the particles and see how the blast evolves. Okay, but then that's of course very complicated. But in a simulation, you can still do it. Okay, and then you can ask if you use the Navier Stokes Fourier equations and again solve this problem for the same initial condition, how does it evolve? Okay, and so we try to compare these two from like just the microscopic model and the hydrodynamic equations, and ask how do they compare? Okay, and what we find at this, so there are interesting results which you can read in some of this work. So I'll stop here. Thanks.
Thank you, Abhishek. Let's thank Abhishek for the nice talk. We should soon organize another talk for you to give the second part.
Yeah, actually, I'm quite excited about this other part. I mean,
Yeah,
that's the
maybe
sort of, yeah.
do that. Now the talk is open for questions, and people who are online, just raise your hands, and in person, can you get the mic to Vijay? And in the meantime, Shopto Sindhu online, you can unmute yourself and ask the question.
Thank you, sir. Thank you, sir, for the nice talk. I have a question. This in one slide you talked about this Green-Kubo relation, that Green-Kubo relates kappa to the integral of current correlation. So my question is that, like, is this Green-Kubo relation valid in all dimension and all kind of like linear or and non-linear heat transport, or is there some kind of boundation?
Yeah, so the Green-Kubo, I mean, okay, so if you, I mean, when you derive, of course, there's a lot of assumptions in the derivation, but you can write it, of course, in any dimension. But so the Green-Kubo tells that relates the conductivity to an integral of the current correlation. And what you find in one dimensions is that this current, so it's an integral over like all time, 0 to infinity of the current correlation. And in one dimension, what you find is that this correlation function decays very slowly. Okay, like it's slower than 1 over t. So it's a divergent integral. So in that sense, you can understand just from Green-Kubo why you get a divergent, why thermal conductivity is increases with system size. Okay, so that's one way to understand. even within the using Green-Kubo of why in 1 and 2 dimensions you get anomalous heat transport. I hope that answers.
Thank you, sir. Yes.
Yeah. Abhishek, there are other linear macroscopic laws, Newton's law for momentum transport, or so are there anomalous behavior in those things as well?
Okay, I mean, of course, like for diffusion, you know, like for example, self-diffusion in 2 dimension, there's anomalous, right? That's very old result.
I was thinking of momentum transport.
But yeah, momentum transport, I don't know in 2 dimension whether you can like, oh, yeah, 1 dimension of course doesn't make sense, but 2 dimension you can ask, is there possibility of anomalous behavior? I haven't seen any, I don't know of any study.
Okay. No, I was thinking of the connection. If you think of Onsager reciprocity, that if there is anomalous behavior in heat, wouldn't that automatically imply anomalous behavior in momentum?
Yeah, so in 2 dimension, given that thermal conductivity has, now you are saying if I, of course, I don't know if these two are coupled, but maybe, yeah, one can easily find models where there is coupling between moment, this heat and in that case, there could be, I mean, it's possible, right? Yeah. But this is something which no one has actually, I'm not aware of any study.
Or is there some reason why there is anomalous transport only for the heat mode and not for the momentum mode?
Yeah, I mean, so the I mean, heat, of course, is because of the slow decay of the current correlation. Now, I'm not sure if the momentum correlations would.
Momentum also you can write down the Kubo like a stress correlation.
Yeah. So there, I don't know the stress if there is a see. I mean, because this understanding is entirely using this theory, and I don't know if you do that. Probably one can answer, but I don't know the answer. Like one has to do the corresponding calculation for the stress current, and I don't know what the answer is.
Thanks. Okay, anyone else from the?
Yeah, could one approach these problems from the point of view of mode coupling theory? This anomalous transport and.
So I mean so once you write the hydrodynamic equations, then the computation of these correlation functions are actually done using mode coupling theory. So so a lot of the results that one finally extracts is again is using mode coupling theory.
Yeah, I think yeah, that's what usually is done in this kind of framework typically. Okay, thanks.
Okay, Anirban from online.
Okay, hello. So my question is that in this in the fluctuating coarse-grained framework, so everything is done in the coarse-grained. Every variable is coarse-grained. So if I calculate the current correlation using this framework, so also it will be possible that I will get the divergence in the current correlation in the coarse-grained variables also. And first of all, is it at all possible to compute the current correlation using this framework?
Okay, that's a good question actually. So I mean, okay, so the Green-Kubo, if, in there, when you write the current correlation, it's the bare current. Okay, so without any coarse graining, and that leads to a divergence. Okay, so now what you are asking is like if I do a coarse graining and then define a current, then can I still get finite conductivity? Is that your question?
Yes. Yes.
So actually, it turns out that. I mean, okay, so this is some work that in fact we have been doing. I mean, so like in a recent paper, we tried to derive this. Okay, so let's say this, if you want to derive this equation starting from Hamiltonian, then of course here there's a thermal conductivity, right? Now, if this is infinite, then how do you make sense of this equation? So when we so actually when you try to derive it from starting from Hamiltonian and then doing coarse-grained theory, then what you find is that this conductivity is actually given by a Green-Kubo, which involves a sort of coarse-grained current. Okay, and that actually gives a finite conductivity, which we think should be what you should put here in the hydrodynamic equations. Right? Otherwise, of course, it's difficult to write these equations. We are saying the thermal conductivity diverges. I mean, what does it mean then? Okay, so this is like a bare thermal conductivity, and the way to calculate it is using a different definition of the Green-Kubo formula. So I'm not sure if I answered your question, but that's.
Okay, but I am not sure about my another question. So I got the answer. So, but another question is, if I can we go other way around? Because if I start from this equation, so someone says I define this equation. These are my Navier Stokes equation, and I introduced the fluctuation in some phenomenological way. So and I got this equation. So from starting from this point, is it possible that I go the other way around and calculate the current correlation from this equation itself by
Yeah, so this, I mean, of course, is sorry, what I'm doing going wrong. Okay, so I mean, from this fluctuating hydrodynamic equations, you can actually also compute again the current correlation, and you can get. So this is again something you can compute exactly, and you find this 1 by t to the power 2/3, which will lead to a divergence of the measured thermal conductivity.
Okay. Okay.
Yeah, so that is also done using again this mode coupling theory and so on.
Okay. 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 Thanks.
More questions from the auditorium? Anyone online? Shaptashindu, you already asked your question. Do you have one more?
No, sir. No, sir. Thank you.
So if we don't have any more questions, let's thank Abhishek once more for the nice talk.